Our next topic is going to be the Doppler effect. And the Doppler effect is a frequency shift that is caused by the relative motion between the source of a sound and the detector of the sound. If we look at this diagram, the sound source is right in the middle, and it is moving from left to right. Because it's moving to the right, it is decreasing the distance between the previous wave fronts and itself, and so the wave length is getting shorter. Since it's traveling through one medium, velocity is constant. Because the wavelength is shorter, the velocity is constant, the frequency on the right side of the source heading to the right is higher. So if this is my detector right here, if the object was sitting next to it, the frequency that would be heard would be lower than the frequency that's being heard now. If I had a detector on this side, because the source is moving away from that detector, what I see is an increase in the size of the wavelengths. Again, velocity is constant, so the frequency is going to decrease for the detector on the left side compared to what the sound would appear to. So the sound now would be lower than what the detector would perceive if the sound source was stationary right next to it. So here's an object, and we can drag it, and the larger the vector for the velocity, the faster the object will go relative to the speed of sound. Here we can see in the box the relationship between the speed of sound and the speed of the object. As it's moving to the left, it's compressing the waves. Now we'll have the object moving so that it's moving exactly at the same speed as sound is traveling through the medium. And what we see is constructive interference along that leading edge of wavefronts. It's getting thicker and thicker, and so the sound is getting louder and louder. We can also arrange it so the object travels faster than the speed of sound. What we get now is a sound cone. So my favorite scientific cartoonist, Sidney Harris, giving us a cartoon relating to Doppler effect. And the position and the darkness of the letters in the word bubbles gives you an indication of the volume and the frequency that Mrs. Ginsler is hearing as Mr. Doppler walks by. So of course there's an equation that goes with the Doppler effect, and the Doppler equation looks like this. It relates the frequency detected to the frequency produced of sound, and involves both the speed of sound and the speed of the object or the detector, depending on what's moving. So F is the sound frequency produced, F prime is the frequency detected, plain old V is the speed of sound. If we have a source moving, then it's going to be V sub S. If the detector is what's moving, then it would be V sub D. We're going to use the modified version of the Doppler equation. The actual version looks like this. That's a little painful to try and keep track of and remember, so we're going to use the shortened version. So it is F prime equals F times the speed of sound, either plus or minus, depending, either the source or the detector. So it's going to be an approximation, less exact than the actual sound. Let's take a look and see how it works. I have a siren that produces a sound at 525 hertz. So that would be my F. As I'm standing on the sidewalk and the truck carrying the siren travels by me, I hear, so that would be F prime, 542 hertz sound. On this particular day, we're going to use the speed of sound in air is 343 meters per second. What is the speed of my source? So we're going to use our modified Doppler equation, and let's set it up so we have 542 hertz equals 525 hertz. Speed of sound is 343. Now the frequency I hear is higher. Does that mean the object is moving towards me or away from me? Hopefully you selected towards you. So it would be plus the speed of my source over 343 in the denominator. What's in parenthesis determines whether the frequency I hear is bigger or smaller than the frequency created. So I want a fraction bigger than 1 since the frequency I hear is higher than the frequency created. So now I do the math. I'm going to do it the easy way. Divide both sides by 525 and I get 1032 is 343 plus the S over 343 Multiply both sides by 343, I get 354 is 343 plus Vs. Now I do the math, and I get 11 meters per second is how fast my source object is traveling. When we saw the cone in the animation showing the Doppler effect, that cone is called a shock wave. And a shock wave occurs when the speed of the object is greater than the speed of sound. What we have is constructive interference along the edges of the cone, and so that is a very loud or very large amplitude wave. Behind is regular. If we take a look at this example, I have it set up so that we have the wavelength is 20 meters. The wave speed is 30 meters per second, so it's moving a little bit faster than the length of the wave itself. And the speed of the source is faster than the speed of the wave. So this is what it looks like as it's traveling. So a new wavefront is created each time interval, roughly each second, and where that source was created is left as a dot. So what we see is this cone. Most of you have probably experienced this in the form of a sonic boom. And a sonic boom is created anytime an object is moving faster than the speed of sound. You hear a very loud sound that's due to the constructive interference of the wavefronts. So you are on the ground and happen to be standing there as the plane, if that's what is creating this sound wave, is traveling from left to right. When the wave front hits you, that's when you will hear it. So when you hear a sonic boom, it is not an indication that the plane is just now going faster than the speed of sound. It's an indication that that leading wavefront created by its traveling through the air has just crossed your path. Again, a sonic boom is simply when the shock wavefront from the object traveling faster than the speed of sound reaches your ears. Another really easy and many people can create it sonic boom would be cracking of a whip. If you've ever heard a whip snap, you're essentially hearing a little tiny sonic boom. The end of that whip is traveling faster than the speed of sound, and the crack you hear is a little miniature sonic boom. Okay, so when a plane is traveling faster than the speed of sound, it's described as traveling a Mach speed. And German science physicist Herr Mach determined that Mach speed is simply a ratio of the speed of the plane to the speed of sound. If we look at this diagram, at time equals 0, the tip of the plane was right there. And so in some finite amount of time t, the sound wave has traveled from here to here. In that same amount of time, the tip of the plane has traveled from here to here. So the time for each travel is the same. So we can also say that Mach speed can be described as the distance that the plane has traveled divided by the distance that the sound wave front has traveled. And usually that's easier to calculate. You can also, if you have a diagram like this, actually measure it. Take out a ruler and measure those two distances, take the ratio, and you'll get the Mach speed the diagram is representing. Another way that you can do it is this angle can also be determined. If we look at this particular setup, we have a right triangle here. So the distance from the center to the wavefront is simply the radius of that circle. It's the side opposite our angle. Here's our hypotenuse. That's the distance that the plane has traveled. The side opposite is the distance that the sound wave has traveled. And so opposite over hypotenuse is a sine. So the sine of this angle is equal to the distance that the sound has traveled over the distance that the plane has traveled, which is the inverse of the Mach speed. So Mach speed can also be represented as 1 over the sine of this angle. When we look in class, we'll take a look at 2 videos of objects creating shock waves. And that takes us through Chapter 13 and the finishing of sound.